All right, everybody. There's been a lot of name calling, maligning, and slurring against quarantine or social distancing lately. Some of you are even saying that it's worse than prison, and none of us can say boo because none of us have ever been to prison. So I brought a special guest today to somebody who has been to prison to tell you a little bit more about what it's like. Hello, I'm Prison Mike. Do you want to know why I went to prison? I robbed, I stole, I kidnapped the president's son. That's how we talk in the clink like this. You want to know the worst thing about prison? The Dementors. Not like in Harry Potter, they would fly around and try to suck your soul out. And in prison, all you got to eat is gruel. Gruel sandwiches. Plus, you can also eat your hair. But thanks for letting me come here today and tell you a little bit about my life. Take it from me. You kids in quarantine, in social distancing, you got a good life. You got a good life. All right, thank you, Prison Mike, for helping us realize that quarantine is not all that bad. So thank all of you for putting up with my cheap imitation of Steve Carell's character, Prison Mike. Hopefully you're not going too crazy with all of the social distancing and quarantine. Hope things are going well for you. We're going to continue on with our discussion of metabolism today by talking about how we get from pyruvate to acetyl-CoA, and then we'll enter into the citric acid cycle. So last time we got to the point where we had converted glucose into two molecules of pyruvate. What happens next occurs in the mitochondrial matrix with a complex called the pyruvate dehydrogenase complex. And at the outset, I'll just say I've drawn ahead of time a lot of the structures because they're sort of large, and I don't want to spend time on the video drawing structures when you can pause the video to draw them and get them down into your notes, just so things will flow a little bit better. But the overall change we're going to see is that pyruvate is going to be converted into acetyl-CoA. And there are three steps to this process. The first one is the one that is most important for you to understand. I'll show you the structures and we'll draw out a detailed mechanism. The next two steps involve recycling cofactors and recycling the enzyme. And that I will take you through so you understand it, but that's less important to have firmly set in your minds. So the first step, and if you think about the comparison, between acetyl-CoA and pyruvate, we're going to basically have to cleave the bond here between the group in pink, which is going to end up being CO2. And at the same time, we're going to have to convert this carbon over here in purple. Oops. Well, whatever. We're going to have to convert that carbon over there in purple to the oxidation state of a thioester or a carboxylic acid instead of a ketone. So that's why we call this an oxidative decarboxylation, because we're going to lose CO2, but doing so really requires us to also oxidize the ketone from pyruvate into up to the oxidation state of the carboxylic acid or a thioester. So this step involves something called lipoate. This is the, if this group that I'm circling with the laser pointer were a carboxylic acid instead of an amide, it would be called lipoic acid. It has this interesting 5-membered ring with a disulfide linking the ring together. A disulfide is a bond between two sulfurs. And then the overall lipoic acid is linked, if you look, it is linked to the nitrogen of the epsilon nitrogen of the lysine side chain. It may be worth a little bit of review. The lysine side chain has a beta carbon, gamma carbon, delta carbon, and epsilon carbon. So there are 4 carbons in the side chain of lysine, and then you've got the amino group. And here we've tied up that amino group in an amide bond. So this then becomes, this oxidized lipoate becomes a reactive arm that is going to swing between subunits of the pyruvate dehydrogenase complex. So the subunit that does oxidative decarboxylation of pyruvate is called pyruvate dehydrogenase. You can tell it's an oxidizing enzyme because it's got dehydrogenase in its title. There's a couple of, there's a cofactor in this process. It's called thiamine pyrophosphate ylide, and I've drawn the cofactor here. I believe we talked a little bit about the structure of thiamine last time, or maybe in the first lecture on metabolism. Remember that we focused on this portion of the molecule here, which is the business end of thiamine. And remember we said that this carbon in the ring, in the 5-membered ring, and I'm not sure how we number the atoms of the ring. Maybe we go, we'll just sort of choose arbitrarily, but it'll help us talk about the ring 1, 2, 3, 4, and 5. We talked last time about how carbon 5 is nucleophilic and electrophilic at the same time. You've got a negative charge in an sp, in a lone pairs, in an sp2 type orbital, and then you have a low-lying carbon-nitrogen pi star, or alternatively an empty p orbital on carbon, into which you can dump electron density. So this molecule is both electrophilic and nucleophilic at carbon 2. And the product of this reaction is going to be, I guess I should have changed my colors, huh? The product of this reaction is going to be CO2. We will have lost CO2. And that's one of the 3 carbons of pyruvate that we will have lost as CO2. We've got 2 carbons left, and if you look, the purple group that used to be a ketone is now tied up in a thioester with one of the sulfurs of the lipoate. But the lipoate has been reduced. We no longer have the sulfur heteroatom bond, that disulfide. Instead, we have the thiol and the thioester. So we've reduced, and the thioester is just like a thiol that's involved in an ester bond with an acetyl group. So let's talk about mechanism. How does this process happen? We want to talk about it because it's a really great example of the ability of nature to do things that would be otherwise quite difficult to do in terms of the chemistry. So we'll start with the mechanism here. If it's all right, I will simplify some of what we have drawn. For example, with the thiamine pyrophosphate ylide, I'm not going to draw the other groups. I'm just going to put R groups in the various places, and we'll focus in on the business end of this molecule. And what we've got here in terms of pyruvate is we have a ketone, which is going to be our electrophile. And then we have the thiamine pyrophosphate ylide. We can abbreviate that as TPP ylide. And this is going to be our nucleophile. And I told you it's going to be nucleophilic at carbon 2 within the 5-membered ring. So we're going to have that negatively charged carbon attack the carbon-oxygen pi star at the ketone to generate a tetrahedral intermediate, which we're just going to show picking up a proton from some acid. We could show the negatively charged oxygen and then in the tetrahedral intermediate and then show it picking up a proton, but we can condense those two steps together to save ourselves a little bit of time, right? So the tetrahedral intermediate would have looked something like this. But instead of showing that negatively charged oxygen, we've just protonated that oxygen. All right, so let's focus in on the structure of this intermediate. Oops. Because this is really important. I haven't drawn it in a way that looks tetrahedral, so maybe I'll put a wedge. On the other hand, we're not saying anything about what the stereochemistry is, so maybe it's okay to just use the straight lines. Got to make them connect. It may be easy for us to think about how this reaction happens if I redraw this molecule in a slightly different way. So I'm going to start with the carboxylic acid here. Then I'm going to put the thiamine portion of the molecule here. And then we'll put the OH group and the CH3 group here. Does that work so far? All right. I want you to look at the carboxylic acid here. And we'll start with the carbonyl carbon. Now we've got the alpha carbon, and now we've got the beta carbon. If you look at this molecule, we have a carbon-nitrogen group. And actually, it's positively charged. We've got an iminium group. At the beta carbon. And if you imagine that iminium groups have similar sorts of reactivity to ketone groups, this is like a beta keto acid. So having the TPP ylide attack the ketone of pyruvate suddenly turns the acid of pyruvate from an alpha keto acid into something that looks like a beta keto acid. And what can we do with beta keto acids? Do you remember? If you don't, I want you to take a second, pause, and go back to chapter 24 and look up the stuff on malonic ester and acetoacetic ester synthesis, especially the final few steps. You got it? What do we do with beta keto acids? Well, we recognize that they are ready for decarboxylation. And the reason they are ready for decarboxylation is that when the CO2 kicks off the alpha carbon here, when we break this bond, the electrons that would be left behind on the alpha carbon are going to be resonance stabilized. So let's show that process happening. We would take lone pair electrons on the oxygen. They're going to kick down to form the second carbon-oxygen pi bond in CO2. At the same time, we're going to break the bond between carbonyl carbon and alpha carbon. And then shift that, and we can just have the lone pair electrons go on to the alpha carbon, where they will be stabilized by resonance. So that's where we lose our CO2. Maybe it would be helpful to continue to highlight that CO2 group through the molecule. Oops, didn't like that. So here is CO2 that we've lost, and what's left behind is this resonance stabilized enolate that's actually a Zwitter ion. Got the negative charge on a carbon that is alpha to what looks like here something a lot like a carbonyl carbon. And we can draw a resonance structure where we put a double bond between the alpha carbon and the carbonyl carbon of that iminium ion. And then the electrons from the carbon-nitrogen pi bond move out onto the nitrogen. To give you this molecule. So I'm going to highlight in pink this iminium group, and I'm going to remind you that iminium groups are reactive like oxonium groups, that is protonated carbonyl oxygens. All right. So when we remove, when CO2 and the electrons on CO2 kick down and CO2 forms and the electrons in the bond between carbonyl carbon and alpha carbon move over onto the alpha carbon, this whole thing becomes a leaving group, and the reason it can leave is that it's resonance stabilized. This negative charge can move over to become a pi bond, and the electrons in this carbon-nitrogen pi bond can move over to go on the nitrogen. So up here we have a resonance structure that looks like an iminium enolate, and down here we have something that looks kind of like an enol. Trying to figure out how to demonstrate this. Something that looks kind of like an enol but then also kind of like I better choose a different color, sorry folks. Kind of like an enamine. So if we're thinking about the enol, here is the oxygen, here's the carbonyl carbon, here's the alpha carbon. If we're thinking about the nitrogen, here's the nitrogen, the carbonyl carbon, and the alpha carbon. So you have the enol in purple, you have the enamine in green. Okay. Now, if the enol we're going to tautomerize to form the keto form of this molecule, what we would do is remove this proton, electrons would kick down, and we'd protonate or something on the alpha carbon, the purple alpha carbon. If instead we had the enamine tautomerizing, we would have electrons on the nitrogen kick down here to form a new carbon-nitrogen pi bond, and we'd have to move these electrons onto the carbonyl carbon where they maybe could get protonated. So hopefully, if we compare the resonance structures of the iminium enolate, if we compare these two resonance structures, the iminium enolate form and the enol/enamine form, we can see that lone pairs on the nitrogen are delocalized between the nitrogen and green alpha carbon. And that's going to be important for the oxidation step. So if it's all right, I'm going to copy the iminium enolate resonance structure. And I'm also going to copy our oxidized lipoate structure. And this is the stage at which oxidation of what we just called the green alpha carbon happens. Okay, so we're going to take lone pair electrons from the alpha carbon, and we're going to attack. Gotta see where we need to end up. We're going to attack the internal sulfur of our disulfide. This is kind of an SN2 style reaction. That is, you can think of the sulfur-sulfur bond as being weak. Heteroatom-heteroatom bonds are generally pretty weak, and their sigma stars are low in energy, and therefore they're easy to break. So we have our nucleophile lone pair electrons on the green alpha carbon attack the sulfur to create a new carbon-sulfur bond, and then the electrons from that carbon-sulfur bond will pick up a proton from some acid. We don't care what it is. And that will give us the following intermediate. Oops. Sorry, folks, didn't mean to do that. That will give us the following intermediate. So the methyl group's still in place. Here's the oxygen. Here's the bond to the thiamine portion of our molecule. Here's the positively charged nitrogen. And here is our new bond. Sorry, I'm just going to copy and paste to make this easier. With sulfur. Okay, so why is this an oxidation step? Well, let me, for a moment, highlight in green those electrons that were on the alpha carbon. right? They used to belong to the alpha carbon. But as soon as we have the alpha carbon attack the sulfur, we're going to treat these electrons like they belong to sulfur. So in that way, electrons that carbon used to own outright, it is now given to sulfur, and that carbon has been oxidized. All right. Now, as we look at this intermediate, one of the things you might wish to note is that if we circle this portion of our molecule, this portion of our molecule is the thiamine ylide, or rather could be the thiamine ylide, and could be a good leaving group. So in order for that to happen, we'll have a base remove a proton from the OH group, electrons will kick down, leaving group will leave, and that will give us regenerated thiamine pyrophosphate ylide. And then as the product, our reduced lipoate thioester. All right. Let me show you where those thioester carbons come from during the whole process. We sort of labeled things funny here. All right. So what we've done now, if we go back and compare to pyruvate, where we had, let's see, carbon 1, 2, and 3, we lost carbon 1 as CO2, and then now we have carbon 2 and 3. Carbon 2, instead of being a ketone, is now a thioester. All right? So that's the formal oxidation step. We reduce, this process reduces a disulfide to 2 thiols and oxidizes a ketone to a thioester or a carboxylic acid oxidation state. All right. Feel like that was kind of convoluted. You may need to hear it again, so feel free to pause the video and back up and look at it all again. The beautiful concept of using thiamine ylide is that you take the carbonyl you take this alpha keto group. Ketones are usually electrophilic at the carbonyl carbon, right? You want a nucleophile to attack the carbonyl carbon, and that's exactly what's happened here when thiamine ylide does the attacking. But as you follow through, this same carbonyl carbon, after decarboxylation, basically becomes a nucleophile. We've changed what was an electrophilic thiamine pyrophosphate, changes an electrophilic carbon into a nucleophilic one. And this concept of changing a carbonyl carbon into a nucleophilic carbon is a famous one in chemistry, and it's called Umpolung, which is a German word which I have misspelled. and you won't need to know that. But those of you who go on to learn more about organic chemistry will encounter that word again. All right. So the next two steps of our process involve, we've already got a thioester. We need to swap out the lipoate group attached to our acetyl group in orange. We need to swap out this thiol group, the lipoate, reduced lipoate thiol group, for coenzyme A, which has a thiol at the end of it. We've shown you the structure of coenzyme A before. Here is the adenine group. Here's ribose. Here's a pyrophosphate. Here's a pantothenate amide, and here is cysteamine, which is derived from the amino acid cysteine and has this sulfur on it. So we're basically going to replace, we're going to do a substitution reaction where the sulfur from coenzyme A attacks the carbonyl carbon. We get a tetrahedral intermediate, which kicks down and kicks off reduced lipoate thiol as a leaving group. The subunit of the pyruvate dehydrogenase complex that does this is called a dihydrolipoyl transacetylase. It's called a transacetylase because it transfers the acetyl group here from reduced lipoate to be on the end of coenzyme A. So the mechanism is nucleophilic acyl substitution. You should be able to push arrows for this reaction. I expect you to be able to do that. If you can't do it, you need to go back to chapter 22 and remind yourself about how esters work, how acid chlorides work, how anhydrides work. Thioesters react very much like anhydrides do. When you do the nucleophilic acyl substitution, I'll just make a note, see chapter 22 for details. You end up putting the acetyl group on the thiol of acetyl-CoA, and then you liberate the reduced lipoate. Acetyl-CoA then is our entry point into the citric acid cycle. However, the enzyme pyruvate dehydrogenase complex is not done yet because we need to oxidize lipoate, reduce lipoate back up to the disulfide oxidation state, so we're ready to go on another reaction. So our next step is the one that I don't want you to worry about too much, but this step is necessary for recycling the reduced lipoate and oxidizing it back to the disulfide form. And in the process, we do that oxidation reaction mediated by NAD+, which goes to NADH. Of course, you can take the NADH to the electron transport chain in mitochondria, where you can use it to generate ATP by driving the proton gradient. The subunit of the pyruvate dehydrogenase complex that does this is called dihydrolipoyl dehydrogenase. It's called dihydrolipoate or dihydrolipoyl because it's the reduced form. And we're going to dehydrogenate it, meaning we're going to take away one hydrogen with its electrons and another proton and make a disulfide bond. In the end, we've got oxidized lipoate and NADH. The mechanism for this reaction they call a ping-pong mechanism because we're actually going to reform the lipoate disulfide long before we generate NADH. So here is a cartoon of dihydrolipoyl dehydrogenase. There are two key cysteine residues that are involved in a disulfide bond, and the thiol, one of the thiols from reduced lipoate is going to attack this disulfide bond to form another disulfide bond. So we would call this reaction maybe disulfide exchange. essentially it's a SN2 reaction where the thiol on reduced lipoweight gets deprotonated and then attacks one of the sulfurs in the disulfide, and the sulfur-sulfur bond breaks to give you a thiolate on cysteine 46 and a new disulfide between one thiol from lipoate and another thiol from cysteine 41 of the enzyme. They call this a mixed disulfide because the two things on either side of the sulfur-sulfur bond are different. And then we can exchange this disulfide for the lipoate disulfide through another round of disulfide exchange. That is, the other thiol on our lipoate molecule will be deprotonated by a base. Those electrons will then go on to the sulfur will attack. The sulfur will attack the pink sulfur in this mixed disulfide bond, and then the electrons would go from this pink to orange sulfur bond would go on to the orange sulfur and eventually pick up a proton from solvent. So if you look at what we've done, we have oxidized lipoate and we're ready for another round, but unfortunately we've just robbed Peter to pay Paul because now our enzyme is reduced and unable to continue. So recycling of the enzyme takes another couple of steps. And one thing you have to understand about this enzyme is it closely associates with a molecule of FAD, which is an oxidizing agent. And the way FAD reoxidizes this molecule, and this is chemistry that I don't really expect you to know, one of a negatively charged sulfur on the protein attacks this carbon in FAD, and electrons from the electrophilic carbon-nitrogen bond kick up and pick up a proton. That's sort of carbonyl chemistry, right? Nucleophile attacks the carbonyl carbon of an imine, and electrons go up and pick up a proton. Then we get this strange intermediate where we just made a new carbon-sulfur bond. And this is the part where we restore the disulfide because these electrons that used to be on the negatively charged sulfur are now in the sulfur carbon bond. And when the cysteine 41 thiol gets deprotonated and attacks the cysteine 46 sulfur, those electrons that used to belong to sulfur are now in the FAD molecule. They kick down here to form a double bond, and then we pick up a proton on that nitrogen. And in so doing, we recycle the enzyme and we generate FAD H2. And it's these electrons that are the ones we gained. And if we go sort of back to the beginning of this process, those electrons ultimately came from this sulfur. Well, yeah, ultimately came from this sulfur. They made the mixed disulfide, and then so I guess those electrons technically would be in the sulfur hydrogen bond on cysteine 41. And the electrons that do the attacking are these ones that used to be in the cysteine-cysteine bond. So in any case, FAD, through this strange mechanism that, again, I don't expect you to know, recycles the enzyme. And then because FAD and FADH2 are so closely associated with the enzyme, they really don't diffuse away. And instead, we need to do a hydride transfer from FADH2 to NAD+, so that we can make NADH, which does diffuse away and can be taken to the electron transport chain. The mechanism is shown here, and I don't want to spend any time on it other than to say that we transfer a hydride over to NAD+ to get FAD and NADH. And now everything is set. The enzyme has been recycled, lipoate has been regenerated, and FADH2 has been converted back into FAD. And the payoff here is this molecule of NADH, which we get to take off to the electron transport chain. So if we go back and review where we were at the beginning, the overall reaction mechanism is for us to take pyruvate and coenzyme A and NAD+, and out of it we get acetyl-CoA, one molecule of CO2, and one molecule of NADH. All right. So with that, we've generated acetyl-CoA, and that is our entry point into the citric acid cycle. So just to remember, these two carbons are from glucose. The carbonyl carbon used to be the ketone in pyruvate. And the citric acid cycle occurs also in the mitochondrial matrix. And the citric acid cycle doesn't generate a lot of ATP in and of itself, but it does generate NADH as we oxidize acetyl-CoA all the way to CO2, and then we can take the NADH and the FADH2 to the electron transport chain. We do get one equivalent of ATP. GTP, which I drew the structure of in our first metabolism lecture, is basically interchangeable with ATP. So there are 10 steps to the citric acid cycle. We'll call the first step 0 because that's what it said on Wikipedia, and if you go there and look stuff up, I wanted to be consistent, or else I'm just lazy, who knows. Acetyl-CoA, those are the two carbons we have from glucose. Remember that for every molecule of glucose, we made 2 molecules of pyruvate in glycolysis, and then those 2 molecules of pyruvate were converted through the pyruvate dehydrogenase complex into 2 molecules of acetyl-CoA and 2 molecules of CO2. So of the 6 carbons in glucose, we've already lost 2 to CO2. And I will just say that everything that we're going to show happening in the citric acid cycle for one equivalent of acetyl-CoA has to happen again for the second equivalent of acetyl-CoA. So the first step, and the great thing about the citric acid cycle is most of the steps are reactions you should recognize from 351 and 352. For example, the first step converts oxaloacetate, which is a 4 carbon diacid with a ketone on the alpha carbon, converts acetyl-CoA with oxaloacetate to give citrate. And the mechanism for this reaction is basically an aldol reaction. So you're going to use acetyl-CoA as the enolate. You will have some base, we don't care what, probably from the enzyme. Remove the proton on acetyl-CoA to give you the acetyl-CoA enolate, which will then attack the ketone, and electrons from the carbon-oxygen pi bond will move up onto the oxygen. Let's draw what that intermediate would look like. Here is the negatively charged oxygen. Here is the rest of our oxaloacetate molecule. And then here is the acetyl-CoA that we just used as an enolate to attack the carbonyl carbon. And then we would show that negatively charged oxygen picking up a proton from somewhere. We don't care where, perhaps from the enzyme, perhaps the conjugate acid of our base. The product of this reaction is probably has a name, but I don't know what it is. And the last step in this reaction is to do a substitution reaction, nucleophilic acyl substitution, to replace the thioester with an acid. So I'm not going to draw that out. You should practice that and make sure you know how to do it, but effectively we would remove a proton from water. Hydroxide would attack the carbonyl carbon to give you a tetrahedral intermediate. Following that tetrahedral intermediate, the negatively charged electrons would kick down and kick off the CoA thiolate to give you an acid, and then that thiolate could deprotonate your acid, and that would give you regenerated coenzyme A and then citrate. Okay, so aldol followed by thioester hydrolysis. Now, you have a less stable thioester replaced by a more stable acid / conjugate base. And so this step is very downhill in energy. And that is why it is essentially irreversible. The enzyme that catalyzes this reaction is citrate synthase, so named because you're making citrate. Citrate is an achiral molecule. If you look, this carbon that bears the OH group is not a stereocenter because you've got two of the same thing attached, a CH2 and then carboxylate, a CH2, COO-. And so it's at this stage that from now on we're sort of going to lose track of the carbons that came from acetyl-CoA because the carbons in purple are identical to the carbons in orange. It turns out that chiral enzymes can tell the difference between the purple and orange carbons, but that is a level of detail that we're going to ignore. All right, so we've now incorporated two carbons from acetyl-CoA into the citric acid cycle. Now our task is going to be twofold. We need to oxidize some carbons in citrate to the CO2 level, and we also need to regenerate the oxaloacetate starting material. And hopefully I'll be able to illustrate the beautiful chemical strategy that is used in this process. Okay, so if we wanted to lose CO2, what are our strategies for that? What have we seen that can lose CO2 before? Well, we've seen two different kinds of decarboxylation reactions so far. The one we saw previously with the acetoacetic ester and the malonic ester synthesis. That is, we learned that beta keto acids can decarboxylate. All right, that's good. But we've also seen that alpha keto acids can undergo oxidative decarboxylation, just like pyruvate did. But you're going to need TPP illid as a cofactor, you're going to need lipoate, you're going to need FAD, and you're going to need NADH to get that process done. So for our first goal, our first goal to oxidize some of the carbons to CO2, our method is going to be to try to move functional groups around so we either have beta keto acids or alpha keto acids. So much of what we're going to do in the citric acid cycle is going to be about targeting one or the other of these desired functional groups that are ready for some kind of decarboxylation reaction. And then in terms of goal 2, we'll need to wait until we lose those 2 molecules of CO2, and then we'll be ready to talk about how we get back to oxaloacetate. So yeah, we need to oxidize 2 carbons to CO2 level. That'll take us from a 6-carbon molecule to a 4-carbon molecule. And once we get to the 4-carbon stage, then we have to regenerate the oxaloacetate starting material. All right. So the next 2 steps are catalyzed by the same enzyme, and they involve an interchange between 2 isomers, 2 regioisomers. One is called citrate and the other is called isocitrate. So let's look at the structure of citrate. As we showed here, you've got the CO2 minus group, the hydroxyl group on this carbon, and then you have the 2 equivalent branches of methylene group and carboxylate group. Now, think about our goal, which is to get to a beta keto acid or an alpha keto acid. The problem with citrate is, let's identify the carbonyl carbons we have. We've got purple carbonyl carbon, and the OH occupies an alpha position there. Could we make an alpha keto acid out of that? Well, nope. You can't make a purple alpha keto acid because the OH group is on a tertiary carbon. And you learned in 351, you can't oxidize alcohols on tertiary carbons because there's no hydride that you can remove. Okay, well, let's look at the other carbonyl carbons. Let's use this carbonyl carbon in green. There's an alpha. Then the OH group is on the beta carbon. Okay, well, a beta hydroxy group is a start. Could we oxidize that to a ketone and then have a beta keto acid? And again, you can't make the beta keto acid because the OH group is on a tertiary carbon. So that's a problem. And we could say the same thing for the other branch. The carbon with the OH group is beta to the blue carboxylate as well as to the green carboxylate, and in the same way, we can't make a beta keto acid that way. Oops. Because the OH is on a tertiary carbon. So what is our strategy going to be? Well, it's quite simple. We're going to move the OH group over. If we go look at our target molecule, isocitrate, this sort of changes things. Let's see, I believe as we look through here, this is the purple carbonyl carbon. Here's the alpha carbon and purple beta carbon. So if we get to isocitrate, where we've moved the OH group from being on this alpha carbon to being on the purple beta carbon, now we could oxidize that to a beta keto acid, right? We would just need to turn this into the ketone. And in addition, that would also be an alpha sorry, let me just, choose the color blue. That would also, if we were to oxidize that OH group to the ketone, we would also make an alpha keto acid. That's possible. So we can make a beta keto acid from isocitrate, and we can also make a beta keto acid. Oh, just writing the same thing, that's dumb. We can also make an alpha keto acid from isocitrate. So the isocitrate structure sets us up nicely to do our 2 decarboxylation events. So how does this happen? In order to move the OH group over 1 carbon from purple alpha to purple beta, we're going to use an enzyme called aconitase, and we're going to go through an intermediate called aconitate. Essentially, what we're going to do is E1CB elimination. This is like, do you remember how when we have an aldol, aldol reaction generates a beta hydroxycarbonyl group? In blue shows the numbers in blue, or the letters in blue highlight the beta hydroxycarbonyl group that we just put in from acetyl-CoA. Getting rid of that OH group to do the dehydration reaction is as easy as the E1CB elimination that we've done previously. That is, you have a base, we don't care what it is, probably from the enzyme, remove the alpha proton to generate an enolate. Shrink. And once you've generated that enolate with negative charge on the alpha carbon, then those electrons can kick down and eliminate the OH group. And that OH group may pick up a proton on the way out, that's fine, but doing so creates a new pi bond between blue alpha and blue beta. So let me continue to label things. C alpha beta, C. And the resulting molecule is called cis-aconitate. It's not necessarily important that you have these 2 carboxylate groups on the same side of the double bond. That's how it actually is, but it's not important for you to remember that. The cis-aconitate molecule is interesting because it is a two-faced alpha beta unsaturated carbonyl compound. And we could use water as a nucleophile. If we remove a proton with base, the OH group could attack at blue beta carbon. If it did, that would just take us back to citrate, and this is an equilibrium reversible process that happens all the time. But cis-aconitate is also alpha beta unsaturated from the purple point of view. If we start with the purple carbonyl carbon, then an alpha carbon, then a beta carbon. And so it is also reasonable for OH minus to attack purple beta carbon to give us an enolate with negatively charged electrons on the alpha carbon, which would subsequently get protonated by some acid, perhaps the conjugate acid of our base. If we have hydroxide attack the beta carbon, what we end up with is isocitrate. Okay, so just paying attention, I've redrawn the molecule to make it a little clearer. The OH group used to be on purple alpha carbon. Now it's on purple beta carbon. Carbonyl carbon is here. So now our OH group is beta to the purple carbonyl carbon, and now it is also alpha to the blue carbonyl carbon. So isocitrate is now nicely set up to make beta and alpha keto acids if we oxidize the OH to a ketone. So, unsurprisingly, that's going to be our next step. Step 3 and 4 sort of occur together, and they're catalyzed by the same enzyme, isocitrate dehydrogenase. We're going to oxidize the OH group on isocitrate using NAD+, and the mechanism for that is going to involve a base removing a proton from the hydroxyl group. Electrons kick down from that oxygen to form a new carbon-oxygen pi bond. Hydride leaves, but by leaves we mean is delivered, handed off directly to NAD+, and we've seen NAD+ based oxidations like this in the past. That generates this intermediate oxalosuccinate, which is, as we pointed out just a few minutes ago, a beta keto acid. And here is our first equivalent of NADH from this process, the first sort of payoff from the citric acid cycle. We can take this to the electron transport chain and generate 2.5 to 3 ATPs. All right, what happens next is a simple decarboxylation reaction. The reason the molecule can decarboxylate is because what's over here on the other side of this bond between carbonyl carbon and alpha carbon, that's a decent leaving group. So electrons on the oxygen can kick down to form CO2. We could show electrons from the bond between carbonyl carbon and alpha carbon kicking down here to form a pi bond, and then up there to form an enolate. So let's draw that enolate. And I'm not sure whether that enolate gets temporarily protonated on the oxygen to give you an enol, and then after that it tautomerizes to the ketone form, or whether that enolate just gets protonated directly on the alpha carbon. And either way is fine. If you want to draw an enol and then tautomerize the enol to the keto form, you can. Decarboxylation of beta keto acid, protonate, resulting enolate on alpha carbon. And once we do that, we've lost our first molecule of CO2 from acetyl-CoA. And of course that happens twice for every molecule of acetyl-CoA we start with. I don't know what color I'm looking for. So with the two CO2s from the pyruvate dehydrogenase reaction and these two CO2s from going from isocitrate to alpha-ketoglutarate, we've accounted for 4 of the 6 carbons from glucose being released as CO2. Now we've got alpha-ketoglutarate, which is, as just see, keep labeling things the same way we did above. Carbonyl carbon, alpha carbon. Alpha-ketoglutarate is an alpha-keto acid, just like pyruvate. So actually the mechanism for this step you have seen before in the pyruvate dehydrogenase complex. Ultimately, we're going to use alpha-ketoglutarate, NAD+, and coenzyme A. We're going to use TPP to attack the thiamine pyrophosphate ylide to attack the carbonyl carbon. That's going to generate an intermediate that can decarboxylate, can lose the CO2 group. And then we will use lipoate to convert the alpha carbon from the alpha-ketoglutarate into a thioester. And then we'll do thioester exchange to put that alpha carbon that used to be a ketone attached to coenzyme A as a thioester. So we've oxidized from ketone to, and this is our what used to be our alpha carbon. Now we've got a thioester. In the process, as I said, we're going to lose our last 2 equivalents of CO2. This process happens twice, as we've mentioned before. Once we have the reduced lipoate, as we did in the pyruvate dehydrogenase complex, we're going to recycle that with FAD to FADH2, and then FADH2 will donate a hydride to NAD+, to give us the other molecule that I neglected to write as a product, which is just NADH. So I won't draw the mechanism here. I want you to go back and make sure you can do the first step of that the first phase of that 3-phase pyruvate dehydrogenase complex. The one, and maybe the first 2, the one where thiamine pyrophosphate attacks the ketone, you get an decarboxylation, and an intermediate that attacks the disulfide in lipoate, and then the thioester exchange to go from lipoate-linked succinyl-CoA to lipoate-linked succinate group to succinyl-CoA. All right, so now we've got a 4-carbon unit, and we need now our goal. We have a 4-carbon unit. We need to get back to oxaloacetate. And just to remind you, the structure of oxaloacetate looks like this. Same 4 carbons, only we need to turn carbon 2 from a CH2 group into a ketone. So everything we do from here on out is going to be about introducing an oxygen at carbon 2 and then oxidizing it to the ketone. However, the thioester, it would be a shame to waste that thioester group. The thioester is a high energy, very reactive functional group. And it would be a shame not to use that for something. And so it turns out we're actually going to use the thioester to make an equivalent of ATP. The enzyme that does this is called succinyl-CoA synthetase. That is named for the reverse reaction where you take succinate, GTP, and coenzyme A and then make succinyl-CoA. Frankly, there's a lot of enzymes that are named in this sort of strange way. Basically, what will happen is lone pair electrons from inorganic phosphate will attack the carbonyl carbon of succinyl-CoA thioester. That will generate a tetrahedral intermediate that looks like this. OPO3 2 minus there. I guess we lost a proton somewhere along there and we don't, shoot, fine. I'll make sure we get it all right. So here's your phosphorus. Here's the oxygen that did the attacking. Here's the phosphorus. Electrons will kick down and kick off the CoA thiolate. The resulting product will be, sorry folks, the resulting product will look something like this. And then I suppose the CoA thiolate can pick up the proton from the phosphate group. Doing so, and I don't want to redraw that because my arm hurts. Doing so gives us this molecule, which is a a mixed anhydride, where one side is a carbon and the other side is a phosphorus. And we're basically going to bring GDP with its beta phosphate group as a nucleophile. The mechanism isn't this simple, but in effect, we're going to have one of the oxygens from GDP attack this phosphorus, and carboxylate leaves as a leaving group. Now, it turns out it's more complicated than that because the thing that does the attacking of the phosphorus is a histidine side chain in the enzyme, and then GDP attacks the phosphorus on that histidine side chain, and that regenerates GTP, which is interchangeable with ATP. So you should understand the mechanism for how the phosphate group does nucleophilic acyl substitution to replace the thioester with a mixed anhydride, and you should understand how that mixed anhydride is a decent enough electrophile for us to transfer the phosphate group ultimately onto GDP to get GTP. We're using this high energy thioester group to generate another high energy phospho and hydride group in GTP. All right, so that liberates succinate, but we've still got a problem. We need to convert somehow carbon 2, and actually carbons 2 and 3 are identical, we need to somehow oxidize carbon 2. We need to get it up to the ketone oxidation state. So what happens next is FAD mediated. So let me go up a couple of spaces. And I realize this video is running long, but I figure for completeness, let's just have all of the citric acid cycle in one spot. You don't need to watch it all in one sitting, but we're close enough to done that we should just proceed. And here FAD is closely associated with the enzyme succinate dehydrogenase, which I believe is actually embedded in the mitochondrial matrix, along with this molecule called ubiquinone. It has a long terpene tail that helps it associate with and flow freely through the membrane. What will happen in this reaction is basically an E1CB elimination of a hydride. So we're going to deprotonate one of those alpha carbons to generate an enolate. The resulting enolate will do an elimination of a hydride group, which will be handed off directly to the nitrogen of FAD, and we'll push the remaining arrows like this. New nitrogen-hydrogen bond, break the carbon-nitrogen pi bond, form a new carbon-carbon pi bond, break the carbon-nitrogen pi bond, and pick up a proton from some other source. That will give us the desired product, which is fumarate. I can't help but think when I see the word fumarate of the Spanish verb for smoking, which is to smoke, which is fumar. I'm going to roll my R's and try to sound like I'm trying to sound authentic. Yo fumo, tu fumas, usted ella fuma. Fumamos, we. Anyway, so let me, I messed up, guys. I need to draw for you the structure of FADH2. Oh, man. Experiencing all kinds of painful technical difficulties here. So this is FADH2. And then it will turn out that FADH2 will transfer its electrons, transfer a hydride to ubiquinone. And that process will happen something like this. A base will remove one of the protons from FADH2, and hydride will be delivered. And this is basically the reverse of having FADH2 accept a hydride. Hydride will be delivered to that oxygen, and the reason that can happen is because doing so restores aromaticity, and then we can protonate that group, and that's going to regenerate FAD plus. Now the thing that has the hydride is this molecule ubiquinol, and ubiquinol is embedded in the mitochondrial membrane and can deliver electrons to the electron transport chain. Now that we've got fumarate, notice that fumarate is an alpha beta unsaturated carbonyl compound. We are now ready to install an oxygen, and it's actually doubly alpha beta unsaturated. So we're now having oxidized succinate to fumarate. We can now have a base. We don't care what it is. Remove a proton from water, and then water can attack at the beta carbon. Oops, sorry. This is conjugate addition of OH minus to an alpha beta unsaturated carbonyl compound. Afterwards, you protonate the resulting enolate. And I'm not going to show that. Hopefully those arrows provide you sufficient detail to draw the enolate, which you can then show being protonated to give you this now alpha hydroxy acid. It is called L-malate because of the stereochemistry at the carbon that bears the OH group. But now we're totally set up to oxidize that OH group to a ketone, and that's going to take us back to oxaloacetate. So our final step is hydride delivery of from L-malate to NAD plus. And that will give us another payoff, but will also regenerate the oxaloacetate starting material. And we will be ready. We will be ready for the next turn of the citric acid cycle. So here's proton removal, double bond formation, hydride delivery to NAD plus that you've seen before. That reaction is done by malate dehydrogenase. It's reversible, and that gets us right back to the starting point. So we've generated through this process 3 equivalents of NADH for every equivalent of acetyl-CoA, 1 equivalent of GTP, 1 equivalent of FADH2, and we've lost 2 CO2s. And of course, for every turn of this process, for every glucose molecule, we need to go around the citric acid cycle twice. Rather, we need to put 2 molecules of acetyl-CoA through the citric acid cycle. And so we can go back to our original equation those many pages ago. Oops. Sorry if I'm making you dizzy. If we have 2 molecules of acetyl-CoA, we would need 6. We would need if we use 2 molecules of acetyl-CoA, we're going to get 4 molecules of CO2, 6 molecules of NADH, 2 molecules of FADH2, 2 molecules of GTP. And of course, if you make the calculation that for every molecule of NADH, you can get 3 molecules of ATP, theoretically, that's 18 ATPs. For every FADH2, you can get sort of 2 molecules of ATP, so that would be another 4 of ATP. Then you've got 2 GTP sort of equivalents. Add it all up, and we basically get 24 molecules of ATP from our 2 acetyl-CoA molecules. And so the citric acid cycle really does help us to generate more ATP than glycolysis did. All right, with that, we'll call it a day. Next time, we'll talk about fatty acid beta oxidation. So stay tuned. Until then, stay safe, stay healthy, stay organic, and just remember, you gotta